Okay, we can start now because the recording is in progress. So,
Hello everyone, we welcome you all for joining us today in the year-long program at Bhaskaracharya Pratishthana. Today we have Guhan Venkat with us who will speak on the Galva representation attached to the elliptic curves over number field. Guhan works basically in Iwasawa theory and on L functions. He has written half a dozen research papers in journals like Transactions of American Math Society, Documenta Mathematica, and Journal of London Math Society. 10 years ago, he was a visitor at BP during his undergrad at ISER Pune. He did PhD from University of Bordeaux and University of Padua through the Algant Doc framework. What is that maybe? He can explain. After PhD in 2015, he worked at places like University College London, University of Warwick, Quebec, and Beijing for his postdoctoral work. Last semester, he joined as an assistant professor under Inspire faculty program at Ashoka University. If he plans to talk on the Galva cohomology and Selmer groups also. And over to you, Guhan. Welcome again.
Yeah, thank you, Devendra, and thanks to all the organizers for this invitation to this talk. This was quite an elaborate introduction. Yeah, as like Devendra mentioned, when I was a student at ISER Pune, this was from 2007 to 2012, and we would often come to Bhaskaracharya to whenever there was a seminar or visitors would come. I think briefly also Vijay Patankar was at Bhaskaracharya, and he ran this sort of a study group on modular forms. So it really warms my heart to be a part of this wonderful program, although virtual, and I hope I'll be able to visit Pune soon. I apologize, I couldn't attend the first two talks in this trimester, but then I watched the YouTube videos, and it appeared to me that a lot of what I wanted to say was already covered in Professor Suri's and Anvesh's talk. But in any case, this is fairly expository talk, so it should be easily accessible. And I'll sort of give a slightly more elaborate introduction to elliptic curves, but then this won't be hard on algebraic geometry. Right? So let's start with cubic curves. So let's fix K to be a field. For now, I won't make any specifications on the type of field we want. And then consider cubic curve defined this homogeneous polynomial over K, say of the form, so let me call this curve as C. It's given by y square z plus a1 xyz plus a3 yz square is equal to x cube plus a2 x square z plus a4 xz square plus a6 z cube. So let me call this as equation 1. I'll keep coming back to this from time and again, at least for first about 5-10 minutes of this talk, right? So here, when I say this is a polynomial over K, I mean that these coefficients AI are all from the field K. Yeah, so this should be clear that this is a homogeneous polynomial, so it cuts out variety in the projective space, or in other words, if say x naught, y naught, z naught is a solution of this equation 1, then also lambda x naught, lambda y naught, and lambda z naught is also again a solution. Let's say for the moment that I consider that lambda is not equal to 0. Of course, there's also the trivial solution, which is just 0, 0, 0. And we sort of want to discard this to sort of get something nice in the projective space. Yeah, discard this. So then it makes sense to only restrict to sort of non-zero scalar multiples of these solutions. Yeah. Or so essentially I'm saying that I'm thinking of these intermediates x, y, and z as projective coordinates. And another interesting point on this curve is the point, let me call this O, which is given by the coordinates 0, 1, 0. Yeah, so this is it's called the point at infinity. Of the curve C. And quick remark is that the point O is the only point on the curve C. Only, yeah, okay, I should mention that this is the non-trivial point on the curve C for which the z coordinate is 0. And yeah, so essentially what I mean by this is that, of course, 1, 0, 1, 0 is a solution, which will also mean that any 0, lambda 0 for lambda not equal to 0 is again a solution. And then you sort of want to identify such points. Yeah. So if you do that, then this point at infinity is the only non-trivial point for which z coordinate is 0. Yeah. All right. So now suppose x naught, y naught, and z naught is a solution to this equation which defines C, and suppose z naught is non-zero, which we know happens for all other points other than the point at infinity, then I can sort of scale down these coordinates, right? Then x naught by z naught, y naught by z naught, comma 1 is again a solution to. Essentially here I'm taking this this factor lambda to be 1 by z naught. And why we do this is that once we sort of isolate this point at infinity, then all other solutions can be of this form x naught by z naught, y naught by z naught, comma 1, and then we can dehomogenize this equation that I wrote above. Yeah. So this. Then I'm going to call this straight away as E, and then but then I'll make a formal definition of an elliptic curve in a short while. Yeah. So I get an equation of the form y square plus a1xy plus a3y is x cubed plus a2x square plus a4x plus a6. Yeah, so I'm going to call this equation 2, where here I've substituted it's a change of coordinates. So y is going to be upper script y by upper script z, and then x is going to be upper script x by upper script z. So any questions or comments so far? Yeah, there's everything on the chat seems to be relevant to the Lime streaming. All right. So once I dehomogenize this cubic curve to this following form. So this is called the Weierstrass equation or Weierstrass form. Yeah. And the reason we do this is I'm going to define the following important sort of quantities associated to this curve E. It's a bunch of numbers. So let's call B2 is A1 square plus 4A2. B4 is 2A4 plus A1, A3. B6 is A3 square plus 4A6. And then B8 is finally A1 square A6 plus 4A2 A6 minus A1 A3 A4 plus A2 A3 cube minus A4 square. So I'm just defining these, but yeah, some of this will show up later, but not all. But anyway, all right. So then C4 is going to be B square minus 24 B4. And then C6 is going to be B2 square. Sorry, this is a B2 here. Yeah, B2 square plus 36 B2 B4 minus 216 B6. And sort of all these quantities lead to defining this very important quantity called delta. So it's you can also denote this as delta E, which is given by minus B2 squared B8 minus 8 B4 cube minus 27 B8 square plus 9 times B2 B4 B6. And finally, I'm going to define J, which is, I'll also denote it as J subscript E, to be as C4 cube by delta. Yeah. So we had this Weierstrass form for this curve E, and then delta is nothing but the discriminant of this. Yeah. Discriminant of this Weierstrass equation. So it's called the discriminant of this curve E, and then J is it's called the J invariant of E. So I'll briefly explain why what's the invariance associated to this quantity. Yeah. So an important thing to note is that E is non-singular. It's a non-singular curve if and only if delta is non-zero. Yeah? So I can straight away make this following sort of a rundown definition of elliptic curve is that an elliptic curve E over a field K is a curve given by an equation in the Weierstrass form. So y square plus a1 xy plus a3y is x cube plus a2 x square plus a4x plus a6. Yeah, where I want that AIs are elements in the field K, and the discriminant of this elliptic curve should be non-zero. So it's a non-singular curve. Yeah. Okay. And then a solution, yeah, x naught comma y naught to, okay, so I'll still continue to call this as equation 2. Yeah. So will be called point on the curve. Yeah. And if it so happens that both x0 and y0 take values in, you write this as k cross k. Yeah, so both x0 and y0 are elements of the underlying field k. Then we say that the point P, x0 comma y0, is a k rational point on this elliptic curve E. All right. So far there's no restriction on this field k, but then now if now suppose the characteristic of this field k is away from 2 or 3. Yeah. So then we can do a change of coordinates. We can replace sort of for the defining. So we can replace x comma y in this Weierstrass form by x minus 3b2 by 36 comma y by 216. This is where these quantities b2n's come into play. And to further simplify, so once we do this, we can sort of put this equation of the elliptic curve in a much simpler form. Yeah, to further simplify this equation 2 as square is x cubed minus 27 c4x minus 54 c6. Yeah, so then we get the following identities that 4b8 is b2 b6 minus b4 square, and then 1728 times delta, which is the discriminant of the elliptic curve, is c4 cube minus c6 square. So that, you know, for people who've, I'm sure all of you know about modular forms, so there's already the parallels between.
So how this number 1728 coming? Yes, can I elaborate one?
Yeah, so 1728 is I don't know much about this, but it's the J invariant. So it's, you know, you have the J function and it's J of square root of -1. So that's how this comes in. But also, I mean, so this is sort of the philosophical understanding, but you do the direct computation and then it'll come out. I don't know, maybe someone from the audience would know more.
Does this changes with the elliptic curve or it remains always for any elliptic curve? Because this quite seems universal constant in this business.
Yeah. So there's no change to the elliptic curve. Yeah. Still, so the geometry of the elliptic curve doesn't change by this change of variables. Is that okay?
Again.
Is the simplified form unique?
I'm sorry, there's some echo coming in.
I think the question was, is the simplified form
unique?
Yeah, I mean, yeah.
Okay.
Yeah. So yeah, maybe I'll call this as 2 prime. But yeah, so I mean, there are several experts in the audience. So is there a philosophical reason why 1728 pops up?
Do you hear me?
Yeah.
Really, I'm not sure, but if I remember truly, this quantity 1728 is for the J invariant, such that J invariant has a pole, and this quantity make the residue to be 1.
Yeah.
If I remember truly.
Right. Yeah. Okay. Okay, so that's sort of a very sort of crash course introduction to elliptic curves. But anyway, I want to also discuss about the group law. Right, so the set of points on an elliptic curve, they form a group. Yeah. So suppose E over K is an elliptic curve over a field K. And for, say, L, any extension of this field K, we shall denote by E of L to be the set of L rational points on the curve. Yeah. So once you have this curve defined over a field K, you can sort of look at extensions of the field, and then you can ask what sort of points from this field are in the elliptic curve. Yeah. So what we know immediately about this set of L rational points is that it is non-empty. If L is non-empty, so there's always at least one rational point, and this is quite trivial because the point at infinity, O, is an L rational point for any sort of extension of the base field K. Yeah. And further, this will also form a group. So, because this is sort of the layman's explanation of the group law. So assume for now that L is the set of real numbers. So that way I can sort of plot this elliptic curve on the real plane. Yeah, so you can sort of have look at the graph defined by this elliptic curve. So this is just the real plane, and then let me look at the elliptic curve given by y square equals x cube minus x plus 1. So this was the elliptic. I think this was the elliptic curve also in the flyer that that was put out for this talk. So the graph looks like this. And I'll sort of explain the group law. So suppose you choose any 2 points, say P and Q. And then what you do is, step 1 is to look at the line joining P and Q in this real plane. And by Bezout's theorem, it will intersect this elliptic curve at a third point. Say, suppose I call this point as R. So it's a point on the elliptic curve. And then let me drop a parallel line to the y-axis. Yeah, so you think of this as the line joining R to the point at infinity. Yeah. So this is on the real plane, but then if you thought of it as in the projective sphere, then you can think of the point as infinity. And then you drop the line joining the point at infinity to this point R. So again, by Bezout's theorem, it will intersect the elliptic curve at the third point. And I'm going to call this point as P plus Q. Yeah. And similarly, sort of sticking on with the same elliptic curve, suppose you want to add P and P itself. So then you take the tangent to this elliptic curve. It will intersect the elliptic curve at another point. Let me continue to call this R, and then you drop the parallel line, then intersect the elliptic curve at a further point, and then this is going to be my point 2P. Yeah. So there's also an algebraic description if if this is not very convincing, but yeah, I'll not go into this. But anyway, I thought since the flyer had this elliptic curve, I'll sort of somehow fit this in. The other graphic on the flyer was that of a torus, and the reason how this connects to elliptic curves is that when we look at elliptic curves over the complex numbers, then the structure of the group of complex points on the elliptic curve is very well understood. So the structure of E of L, which is just the complex points on the elliptic curve, is well known. Again, it fits in nicely to the theory of Riemann surface. Is there a comment or?
So
Okay.
I have a question, Guhan.
Yeah.
So when you consider it over C, then the concept of the rational point is stands separately there, or when you say K rational point or L rational point. So how you distinguish complex point and rational point? Thing.
No, so I mean, if the elliptic curve is defined over C, right, then you can make sense of the complex points on the elliptic curve.
That means that move the field.
Yeah, yeah. Okay, so maybe okay, so I'll make a quick fix to this. So suppose my K is also C. Yeah. I mean, even otherwise, this works, but anyway. So let me write down this theorem. So let E be an elliptic curve over the complex numbers. Then what we know is that there exists a lattice. Let me call this lattice as lambda E. Yeah. So lambda E is isomorphic to 2 copies of the integers. And there is an isomorphism of, it's also at the level of Riemann surfaces, but then, this, we're talking about the group law on a elliptic curve. So there is an isomorphism of Abelian groups, which is that the group of complex points on the elliptic curve is isomorphic to C mod lambda E. Yeah. So C mod lambda E, this is a torus. So you can think of it as S1 cross S1. Yeah. And then the isomorphism is given as follows. Yeah, so the point 0 is mapped to the point at infinity of the elliptic curve. On the elliptic curve. So let me call this as OE just to make this distinction. And then any complex number is mapped to, yeah, on my notes, I had the isomorphism going the other way. So now the arrows are going in an unconventional manner. But anyway, that's fine. So this is Z is mapped to Weierstrass function. Let me call this rho Ez, comma, and then its derivative. So I wrote down the, yeah, so the Weierstrass function is given as follows. So rho E of Z, it really depends on the lattice. Yeah. It's given by 1 over Z square plus summation over all non-zero points on this lattice. Yeah, so Yeah, so this function converges locally, uniformly, absolutely. Yeah. So yeah, so this is just a quick introduction, but of course, I wouldn't say more interesting, but certainly more interesting to me is the following theorem of Mordell-Weil, which happens when you look at elliptic curves over number fields. So let K be a number field, and say L over K is a finite extension. Then for any elliptic curve E over K, we have a nice structure theorem for a set of L rational points on this elliptic curve. So E of L, we know that it's a group. It's actually a finitely generated abelian group. Yeah, so I have this isomorphism to say there's a free part, ZR, and then there's a torsion part to this group, and then this rank R is called the algebraic rank of the elliptic curve, and sort of connects to the Birch and Swinnerton-Dyer conjecture, which says that you look at the L function attached to, you think of the elliptic curve is defined over K, so you can sort of do this base change. So you can think of it as an elliptic curve over the field L, and you can define an L function, look at its order of vanishing at S equals 1, and then the Birch and Swinnerton-Dyer conjecture predicts that these ranks match. But anyway, this talk is on the Galva side, so let's sort of move on to the Galva action on elliptic curves. Yeah. So for now, sort of apply more. So far, we've only we've had some liberty on the fields, but now let's say K is either a number field or a finite extension of field of p-adic numbers, P, or just a finite field. And then once I have this, I'm going to fix an algebraic closure of K and call it K bar. And yeah, as before, let's say E is an elliptic curve over the field K. Okay. So now let me choose a point P on this elliptic curve, right? Let's say it's a K bar rational point. And we know that this elliptic curve is given by a Weierstrass equation.
Let's just take K to be rationals.
Yeah.
What is the structure of the real points on the elliptic curve?
Oh, I don't know about the real points. Yeah, I really don't know.
Is that just a circle or?
I mean, it's an abelian group.
Yes.
Yeah, but I don't know if there's any finer
So it's a
structure
real
on.
group.
Yeah. Yeah, somehow. Yeah, I don't know if there's any further structure. Anyone? I don't. Raghuram or Katre might know this.
I don't know if there's any good answer. I mean, the curves that you drew, for example,
Right. Yeah.
those are the real points, and that sometimes they might have two connected components also.
Yeah. Yeah.
Right?
Yeah.
More than one
Yeah.
connected component.
Yeah. Like.
And yeah,
this
okay,
curve.
one or two connected components is right.
But no
I have
finer
another
structure.
question.
Mm-hmm.
Hi. Uh, uh, what about the group of rational points of elliptic curves defined over function fields?
Yeah,
Is it also something like finitely generated Abelian?
No, I don't know if there's a model equivalent of model Weyland function fields. Somehow that's that's been
yeah, okay. I never read anything.
I've never looked into it.
What goes in the
Function
proof
field.
of the model will need geometric argument?
So for at least over Q, you look at E of Q by, you take the n torsion points on the elliptic curve. So I was just going to define this in a couple of minutes. And then you look at this quotient E of Q by n EQ, you can sort of project this into a Selmer group. And then you sort of deduce this. So there's some geometry, there's also some Galva theory. So that's where sort of this having this
First
number
time
field.
this was observed by Poincaré.
Poincaré, really?
Yeah.
Okay. But I see. Yeah, it's quite interesting. Yeah, it's been a while since I looked at the proof of model Weyl, and of course I'm teaching this course on elliptic curves in a week's time. So through the course I'll get back to the proof. But yeah, it slipped out of my mind now. Okay. Any other questions or remarks? Okay. All right. So let me start with this point. It's a k-bar rational point. So then we know that it satisfies this Weierstrass equation.
So topologically, elliptic curve is a torus.
Elliptic curves over complex numbers, yes.
Yeah.
Yeah.
It's a torus.
Yeah.
Topologically.
Yeah.
So this k rational points, that they could be just finite in the first place, or discrete.
Yeah.
Discrete is the same as finite in this case, because, or otherwise it's dense.
Yeah.
Dense or unless the rank is 1. I see. So,
but you see, this model Weyl theorem, it really needs the field to be a number field. Only then.
Number field. So you take the rational numbers.
Yeah. And so more often than not,
the rational numbers.
Yeah.
But then these k rational points, if the structure is z to the r plus torsion, then how is it sitting in its complex locus?
Right. Yeah.
That is the question. And so if r is at least 2, then that k rational points is a dense subset.
Yeah.
So mildly interesting question is, when is r equals 1 and when is r equals 0, when it is not dense?
Right. Yeah. So more often than not, r is 0 or 1. I think about for 5/6 of all elliptic curves over Q.
So more often it is 0, right? R is more often it is 0.
0 or 1. I don't know what the statistics between 0 and 1, but yeah. So BSD is known for 0 or 1. Almost, in full generality. And then, Bhargava and his collaborators have this statistical argument to show that 5/6 of all elliptic curves, so 83% of all elliptic curves over the rationals have algebraic rank
Is
0
there
or
a
1.
characterization when R is 0 and when is R is 1? Some in terms of coefficients or something?
No, it's yeah. I don't think you can read this off from the model way, from the Weierstrass equation. It's a lot more, yeah,
Oh.
much finer, yeah.
Suppose your K is rationals.
Yeah.
So can you say that for these rational numbers that R is 0 and these
No.
rational numbers is...
No, I don't think so. I don't think you can
No,
read
it's
this
much
off from
more- yeah, it's more complicated. I don't
Yeah.
know. I don't think there's any simple answer like that in terms of those coefficients of that equation.
Yeah. But there are, I think there are reasonable algorithms to, at least between rank 0 and 1, I think you can find this out.
Other question is, can R be arbitrarily large?
Yeah. There are some bounds. I think up to 37 people have found examples, I think. Yeah, rank can go up to 37. Yeah. So yeah, since this has come up, I should mention this. So the LMFDB is, of course, Cremona had this table of elliptic curves before, but now it's become part of this much larger database hosted at
No, but the question is, can R be arbitrarily large?
Yeah, it can be arbitrarily large.
That's a theorem.
No,
Yeah,
that's a theoretical possibility. I don't think it's a theorem.
It's not,
That's a theoretical possibility.
Yeah.
Can it be, is it realized? Can R be 100, 1,000?
No, so I think the bound so far is 37 or 67 somehow. Yeah.
Or is there a bound?
No, there's no bound as yet, but empirical evidence up to R.
Empirical evidence. It's not a theorem. I see.
Yeah. So, yeah, I think 37 roughly. I'm not totally sure about this, but I think 37 norm Elkis had this elliptic curve of rank 37 over the rationals. But yeah, it's a very sparse set of examples. So LMFDB has a lot of examples, and you can play around, compute the ranks, etc. So yeah, it's called the L functions and modular forms database. So this was by John Cremona. All right, so sort of going on, coming back to this question. So
Cremona is the old Cremona?
Yeah, yeah. So,
19th century?
No. He's still around. So.
Oh, he's still around.
Yeah, he just recently retired. So. Definitely not 19th century. This is John Cremona. So yeah, John
this
Cremona.
Cremona transformation, that is different. Yeah?
No, yeah, that's a different Cremona. Yes, all right, so going back to this Galva action. So say P is point on E of K bar, and say I choose a element of this absolute Galva group, sigma. So then I can apply, okay, let me call this equation 3. I can apply sigma on equation 3. And the upshot is that, okay, so I'm sort of also running out of time, and this is quite elementary. So I'll write this as upshot is that sigma of P is also a rational point, K bar rational point on this elliptic curve. Yeah, so essentially we get a GK action. So let me call this as GK for brevity. We get a GK action on this group of K bar rational points. Yeah. So there's an interesting subgroup which came up before also in Suri's talk, is the end torsion points on this elliptic curve. Yeah. So for now, let me say n is at least greater than or equal to 2. And then I can define this subgroup En is going to be the set of k-bar rational points on this elliptic curve E, such that NP, and by NP I mean, you just you have a group law on this E of k-bar. You add, so n is at least 2, so you add this point n times, and I want it, suppose it's the point at infinity. Yeah. So when you think of the abelian groups, it's the points of order dividing n. It's called the group of n torsion points on the elliptic curve. So again, we have a nice characterization of the subgroup. So let K be a field and EA an elliptic curve over the field K. If the characteristic of this field does not divide n, then we know that E of n admits this much nice description, is that it's just Z mod n plus Z mod n, yeah, 2 copies of Z mod n. So in particular, if I choose n to be a prime, then the set of p torsion points is just a 2-dimensional vector space over Fp. Yeah. And we saw that the absolute Galva group acts on all rational points defined over k bar. And we see that, that sort of action descends to n torsion points as well. Yeah. So if P is an n torsion point on this elliptic curve, then for all elements of this Galva group, absolute Galva group, we know that sigma of NP is going to be n times sigma of P, which is just the point at infinity. It shows that sigma of P is again and is also a rational point of is an n torsion point on the elliptic curve. Okay. So there's a link shared by Raghuram. I'll have a look at it. Just after this talk.
Yeah, no, don't worry.
Yeah,
I mean, that's
okay. Yeah.
Ravi Kulkarni's question about the rank, and there is some. So 28 seems to be an example, and things like this. So never mind.
Right. Yeah. No, it's good to know, and all right. So the sort of n torsion points sort of form the genesis for the Galva representation attached to elliptic curves.
For k equals rational, En is always Z mod n plus Z mod n.
Yeah. Yeah. Because you look at points over the algebraic closure of Q. Yeah. So then you sort of have the entire n torsion points. So then it is Z mod n plus Z mod n. Yeah. So now, let me say K is characteristic 0 field. So, I mean, the prototypical example is, a number field, but also you can think of it as a finite extension of QP. So we've already seen that for any sigma in the absolute Galva group, this map P going to sigma P, sigma of P is an automorphism of this of En as a Z mod n module. Yeah. So let me put this down here. So this sort of gives the representation. I'll call this as rho from the absolute Galva group over K to the automorphism module of E of n. So this is also, since we had this nice structure theorem This is also just GL2 defined over Z mod n. So the homomorphism is defined as follows. So any sigma is mapped to rho of sigma, which is the automorphism that maps any n torsion point P. You just apply the Galva automorphism to it. Yeah. And just to be complete, GL2 Z mod n, I mean, is just 2 by 2 matrices defined over, 2 by 2 invertible matrices over Z mod n. Yeah. So how much time do I have? I believe we also started a bit late.
Yes, 5 minutes as per time, but maybe you can extend 10 minutes.
10 minutes? Okay. Okay. So let me.
Minutes total.
15 minutes. Oh, that's great. Okay. Okay. All right. So, I mean, this talk is on Galva representations attached to elliptic curves. So let me give a little bit overview on the sort of Galva representations, not only that come from elliptic curve, but from a lot of objects that will come on later on in this course, like Hilbert modular forms and modular forms as well.
I see.
Yeah, sorry, I'm just ruffling through my notes. Yeah. Okay. There it is.
No, all the real quantities separate.
All right. Okay. So definition, let R be any ring and say K is either a number field or a finite extension of say the periodic numbers. So any P. So for now, there's no restriction. Then a Galva representation is a continuous group homomorphism rho for the absolute Galva group GK to GLNR. So GK, I mean, so the continuity needs some notation. So, I mean, not notation, some explanation. So GK is a topological group. And suppose R has a natural topology, then you give Rn the product topology, and then you think of GLN as an open subset. Otherwise, you give R the discrete topology. And once you have two topological groups, then you can make sense of continuous group homomorphisms. Yeah. So of course, the interesting examples come in when R is either QP or ZP. So these have natural periodic topology associated with them. Or you can have also like mod n representations, more so when n is a prime, but you still have, for example, the representation associated to the n torsion points on the elliptic curve. Then you have, GLN over Z mod. Yeah, okay, so let's say this is an M. Yeah, so M need not be n. So then when you take Z mod M, then you give the discrete topology on Z mod n, and then go on to define such a group homomorphism. All right. So how does this tie up to the elliptic curve? Is that you can define a periodic Tate module of elliptic curves. It will give a nice Galva representation attached to the elliptic curve. Right. So E is going to be an elliptic curve over the field as before, and then say P is a prime. And suppose you choose a point P, which is a P power n+1 torsion point. Yeah. So here, let's say n is greater than or equal to 1. Then PP will be an P power n torsion point on the elliptic curve. Yeah. So multiplication by P sort of gives a nice system of morphism between these subgroups. So I can look at its inverse limit, which I'll call it as TPE. So it's the inverse limit of P power n torsion points. Yeah. So where the inverse limit is with respect to multiplication by P. And we've already seen that EPN is isomorphic to Z mod P power n plus Z mod P power n. So once you take the inverse limit, you get 2 copies of the ring of p-adic integers. So this is called the p-adic Tate module associated with the elliptic curve. And then you can also form what is called as VPE, which is just tensor TPE. It's just allowing coefficients. Yeah. So this will be isomorphic to 2 copies of QP. And then there's also the divisible representation, which is just VPE. So when you look at Iwasawa theory and Selmer groups, this kind of representation is quite useful. Yeah. All right. So we've already seen that so we had this representation n+1. So this is just this is the automorph. I can think of it as the Galva action on the P power n+1 torsion points on the elliptic curves. So we have an isomorphism here. So let me call this as rho E P power n+1. And then I can compose this. I can take the canonical surjection onto GL2 of Z mod Pn. So this again is the automorphisms of the P power n torsion points. And the composition is again the representation afforded to the P power n torsion points. So all these, so the canonical surjections actually are compatible with the Galva action on various P power torsion points. Yeah. So I can also naively define the inverse limit of these compatible system of representations. So what we get is this p-adic Galva representation associated with the elliptic curve. So it's from GK to GL2 over ZP. Yeah. So this was also on the flyer, and you think of this as the automorphism of the p-adic Tate module associated with the elliptic curve, and it's also quite useful to think of this as you can think of ZP as a lattice in QP. So you can look at this injection. So this is called the p-adic Galva representation associated to the elliptic curve. So obviously, the question is, what can we say about this Galva representation? So I'll end my talk in about 5 minutes, if that's fine. 5 to 7 minutes. Okay, so for the rest of the talk, I'll only talk about elliptic curves over the rational numbers. Yeah, and say for now we have an arbitrary Galva representation. Yeah, it's not associated to the elliptic curve. I'll come to that soon. I just want to fix some more notation. All right. So under the absolute Galva group associated to Q, you have the decomposition group at say any prime P. So let me also fix a prime. So this, you know that this is the absolute Galva group of QP. And there's also the inertia group at P. So I'll say that definition, we say this Galva representation rho is unramified at the prime P if the image of the inertia is, it's the identity matrix. Yeah. So the inertia group is a subgroup of the kernel of this group homomorphism. So then we say that, rho is an unramified at the prime P. So once you have an unramified representation, you can think of, you see, you have this short exact sequence of various Galva groups. And we know that the absolute Galva group of FP is generated by the Frobenius. And, let me think of a pre-image of this Frobenius. Let me denote this by sigma P. Yeah. So you can make sense of those unramified of this quantity rho sigma P. So again, sigma P is any lift of the Frobenius. Yeah. And we still call this the Frobenius element at P. Yeah, but still, I'll make the distinction that we call it as sigma P. And once we have that, since it's unramified, the inertia, the image of inertia is just trivial. So you have a well-defined, up to conjugation, you have a well-defined quantity, and then we can also make sense of the characteristic polynomial. Yeah. So we call this a characteristic polynomial at the prime P. Again, I want all this makes sense only if the Galva representation is unramified at P. So I'll call this as phi P of X, which is probably not a good notation because it sort of coincides with the Pth cyclotomic polynomial, but nevertheless. So this is just determinant of 1 minus X, rho of sigma P, where sigma P is any lift of Frobenius. So since the Galva representation takes values in this R by R invertible matrix, the characteristic polynomial is defined over polynomial ring over R. Yeah. So a quick example is that, say L is a prime, and you take chi L to be the mod L cyclotomic character. Again, because I'm short of time, I won't define this, but it's very easy to define. So this is the model cyclotomic character. And what we know is that chi L as a Galva representation, it is unramified at all primes other than L. So you can make sense of the characteristic polynomial at all such primes. So the characteristic polynomial will actually be given as 1 minus px. And of course, the main theorem for this talk is to characterize the Galva representations attached to elliptic curves over Q. Yeah, so E over Q is an elliptic curve as before. And associated to the elliptic curve, we also have what is called the conductor. So conductor, so the primes that divide the conductor are also somehow the primes that divide the discriminant. So the supports are the same. Yeah. And we've already seen that there is this periodic Galva representation attached to this elliptic curve. So it's from GQ to periodic Tate module. So this is just GL2ZP. And the theorem is as follows. Rho EP is unramified. So again, okay, so it's unramified for all primes, not dividing. Also have P, it's a periodic Galva representation. So P is into it, and also the primes that divide the conductor of the elliptic curve. Yeah. So for any, so if L is a prime that does not divide P or any of the primes dividing the conductor, then the image of the inertia group at L will be trivial for this Galva representation. Yeah, so this is the first part. And of course, if you have an unramified representation, the natural question is to ask what the characteristic polynomial look like. So suppose L is such a prime, then the characteristic polynomial so this is going to be 1 minus ALX plus LX square. So here AL is the quantity. You take L plus 1 and then subtract the number of FL rational points on E. So, I mean, so all this, I'm pushing a lot of things under the rug. So we saw that the elliptic curve is defined by a Weierstrass equation. There's also something called the minimal equation. So you can take all the coefficients to be, in this case, integers, because we're looking at elliptic curves over the rationals. So once you have integers, you can reduce the equation modulo any prime, and then for some primes, some good primes, you'll get elliptic curves over finite fields. And then you can look at the points on this elliptic curve over the finite field. So it'll be a finite set because it'll be bounded by L plus 1. So this is a well-defined quantity. Yeah. Okay. So yeah, but it would be criminal not to define what the conductor of an elliptic curve is. So it's essentially all the primes that divide the discriminant with an exponent. So this FL is it's 0 if L is a prime of good reduction. Again, I won't go into the detail of or 1 if L is a prime of semi-stable reduction. And then 2 if L does not divide 6 and E has additive reduction. And then, yeah, there's some sort of a defect that comes in when L is 2 or 3. But anyway, the good primes are the primes that don't divide the discriminant of the elliptic curve. Yeah. Okay, so I think I'll stop here. Sorry, really. Went quite a bit out of time. I also wanted to talk about Serre's open image theorem, but yeah. Maybe I'll stop here.
Thanks, Guhan, for this
Yeah.
nice talk. And
Thanks.
I think this conductor is related with level modular forms.
Yeah, yeah. So, I mean, just getting started with this trimester on modularity, but yeah, the conductor of the elliptic curve will be the level of the gamma naught level of the modular form associated with the elliptic curve. Yeah.
Okay, let's thank Guhan for the wonderful talk.
And yeah, thanks
From the
again
audience,
for
anyone
this.
has any questions?
I have no questions.
I wanted to know how this state module varies with the elliptic curve, sort of kind of invariant or what? Something effect of geometric effect on this.
No, I mean, so Tate module, what do you mean by invariant?
I mean, for every elliptic curve, you associate a Tate module, right?
Yeah, but you see, it's just, the structure is always ZP plus ZP, right?
Okay. Anyone has any questions? I will thank the speaker. It is already late for him by 15 minutes. Okay, so let's thanks again. No questions.
Okay, thank you.
Yeah, thanks. Yeah.
We will visit Pune sometime and to give a in-person talk.
So the talks are every Tuesday and Thursdays, right? No.
Yeah, in this semester.
Yeah, Tuesday, same time, right? 7 to.
It varies with the host also.
Okay, it depends on the speaker.
Speakers also.
Okay.
So Guhan, I guess to qualify the
Oh, okay. So we're back on. All right. So I'll write this down. Yeah, it shouldn't take long. So E over K, elliptic curve without complex multiplication. I won't go into the definition of complex multiplication. So again, here K is a number field. So we had this rho EL. E. Yeah, so then the first part is that rho EL, so the image is of finite index for all primes L. And in fact, it's all of GL2ZL for all but finitely many primes L. Yeah. So, of course, this was Serre's sort of one of his several hundreds of important theorems that he's done in his lifetime. So, the first statement, I think people are interested when it's not all of GL2ZL, right? So there is a complete characterization. So it's either Borel or normalizer of non-split Cartan, right? There are effective versions of when that happens, right? And another important, interesting question is there a bound for the primes? And I think it's sort of uniform. So up to some primes, it's not all of GL2ZL. And then, after that, so what's there are only finitely many primes when it's not the entire, it's not.
Yeah, and that
surjective.
L actually that L depends on the conductor of E.
Right. Yeah. So there are some effective bounds. So there was this. So I was in Warwick as a postdoc, and Samir Siksek had this student Pedro Lemos. Of course, it's not just him, but then he was looking at the bounds for this prime.
Okay. Yeah.
Yeah,
Thanks.
yeah.
So elliptic curve with CM, there should be some result, no? Also.
Yeah, yeah. So then the group will be abelian. You can show that the image will be abelian. Yeah. So it's sort of quite small in GL2ZL. But when it has CM, the Galva representation is quite well understood. Yeah. So kernel of this representation, so it will be a finite extension of K, right? So that will be related to the field with which it has CM. Yeah. So then the image should be abelian. Yeah. That sort of Serre's theorem has, opened up. A lot of people are working on this sort of more effective methods. Somehow I never got a grasp of this, but yeah, it's.
There must be many computer programs to work on this, no?
Yeah, yeah.
And already a lot of information gathered that way. So a lot of data.
Lot of data. Yeah, there are all these very good databases. So yeah, I often a lot of check and just to see how they behave, etc.
I have a very naive question here. So if you know the image of model Galva representation, can we recover the image of full Galva representation? I mean, rho EL.
Well, if you know for all L power n, then yeah, but from L, yeah, I don't know.
Okay.
Yeah, I don't know.
Okay, thanks, Guhan. Thank you.
Okay. Any other?
So the real points is just either empty, either only the identity or the circle.
Yeah, yeah.
Yeah. And
I mean, not the circle, but the graph, yeah.
Its intersection with the
Rational points.
elements of finite order. It's just some Z2 or something like.
Yeah. So Mazur has a characterization on what the torsion part is, right? The points of finite order.
Yeah, but
so it's
the only real points are just Z2, I guess.
Yeah. I mean, yeah.
That's why you don't mention this.
Right. Yeah. Yeah. Real points of finite order. Yeah.
Yes.
Yeah. It's just that one. Yeah.
Okay, Guhan, thanks.
Okay. Lovely. Yeah. So see you all on Thursday, I guess. Yeah.
Yeah.
Okay.
Thank you very much.
Meeting and suggest your student there.
Sorry?
Suggest your student there at Ashoka to join our program.
Yeah. I've told them. Actually, our term starts next week, and I am teaching a course